Hello there, and welcome to the Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind and knowledge becomes a soft lullaby for the night. Tonight's journey will take us somewhere a little stranger than usual, to the uncertain edges of everything we've ever been told about the beginning of the universe. What if the Big Bang wasn't the beginning? What if time itself didn't have a starting point? And what if the discoveries coming from the James Webb Space Telescope, those distant ancient galaxies shining in from the earliest flickers of cosmic light, were whispering something far more mysterious than we expected? But before you settle in and get cozy, I'd love if you could take a moment to like this video and subscribe, only if you truly find these quiet explorations enjoyable, and when you're ready, leave a comment to let me know where in the world you're listening from and what time it is for you right now. It's always such a joy to see all the places we gather from, each in our own little slice of time. Now, feel free to dim the lights, maybe turn on a fan for a soft background hum, and let's gently begin our journey into the mystery of beginnings, or the possibility that there never was one. You've probably heard the story at least a dozen times. 13.8 billion years ago, give or take, everything in the universe, all the matter, space, energy, and time itself, was crammed into an infinitely small point. Then, for reasons no one entirely understands, it expanded. Not into space, but into itself, creating space as it went. This is the standard tale of the Big Bang, a story told in classrooms and documentaries, in science books and quiet conversations under starlit skies. But something unusual is happening. The James Webb Space Telescope, launched to see farther and deeper into the universe's past than anything before it, has found galaxies that shouldn't be there. Galaxies so far away, and therefore so far back in time, that they seem to appear fully formed just a few 100 million years after the supposed beginning. They're not messy or chaotic or half-baked, as we might expect from a newborn universe. They're structured, disc-shaped, heavy. Some are even full of old metal-rich stars. And in the heart of a few black holes as massive as the ones we see today are already spinning, already active, already ancient in a universe that's barely begun. It's as if we turn to the first page of a novel, only to find the characters already halfway through their arcs, already living in a world with rules and histories we don't yet understand. Now, this doesn't mean the Big Bang is wrong. Science doesn't tend to work in absolutes like that. But it does mean something in the model. Perhaps the timeline or the mechanism, or even the idea of beginning itself, may need to shift. And that, in the quiet halls of cosmology, is no small thing. Because if these galaxies are truly as old and massive as they seem, it means either the universe grew up impossibly fast, or it didn't really start in the way we thought. So tonight we're going to take our time. We'll start by walking through the surprising discoveries from JWST. Not in a rush, but like strolling through a garden in the early morning, dew still clinging to the leaves. Then we'll pause, reflect, and look at what these galaxies might mean for our understanding of cosmic time, structure and sequence. We'll explore the traditional model, the Big Bang, dark matter, dark energy, cosmic microwave background, and then gently peel back its layers. We'll step into some of the stranger theories, ideas that have been sitting on the edges of mainstream physics for decades, waiting patiently, bouncing universes, cycles without start or end, quantum fields that ripple in and out of existence, never really beginning because time too might be something that arises only when we look closely enough. Along the way, we'll think softly about what it means to live in a universe that might not have begun. How our sense of time is tied not just to clocks and calendars, but to memory, to motion, to entropy. We'll ask whether beginnings are real, or simply the way our limited minds cope with vastness. And by the end, whether your eyes are still open, or your thoughts have drifted somewhere gentle, we'll return to a place of wonder, not answers, because sometimes the best thing science can offer isn't certainty, but a better question. Tonight is not a debate. It's not about proving or disproving anything. It's a quiet meditation on something that may never have started, and yet still holds us, always, right here. So, let's breathe together. Let your shoulders soften. Feel the earth beneath you, quietly spinning, as it has for billions of years, and let your mind drift to a place where time has no edge, only depth. We'll begin with a telescope that made us wonder again. There's something quietly profound about building a mirror to look into the past. Not just a mirror of glass, but one layered with gold, balanced delicately in the dark, and launched far beyond the warmth of Earth's atmosphere. A telescope not aimed at what is, but at what was. The James Webb Space Telescope is not a machine in the ordinary sense. It's more like a time traveller, a soft eye blinking in the silence of space, gazing across a canvas stretched by light and years and unimaginable distance. It was built with a simple, impossible mission: to look further than any human eye, or machine, ever had. To see light so faint, so stretched by the expansion of the universe, that it arrived as a whisper from when time itself was just beginning to form sentences. The light JWST sees has been travelling for over 13 billion years. It is old, tired light, reddened by cosmic expansion, stretched into infrared wavelengths that only this delicate machine, with its tennis court sunshield and supercooled instruments, was designed to catch. To understand what makes this telescope so special, we first need to understand the concept it was built around: redshift. When something in space moves away from us, the light it emits is stretched, shifting toward the red end of the spectrum. This is called redshift, and it's a little like hearing the sound of a train drop in pitch as it moves away, except here it's light itself doing the stretching. But in cosmology, redshift doesn't just mean motion, it means time, because the farther away something is, the longer its light is taking to reach us. When we observe galaxies at redshift 10 or higher, we are not seeing them as they are now, but as they were when the universe was just a few 100 million years old, a fraction of its current age. In a sense, redshift is not just about velocity or direction, it's a bridge between now and then, a measure of distance and age and the slow unravelling of space itself. Before Webb, our most powerful tool for this kind of observation was the Hubble Space Telescope. Hubble brought us stunning images, unforgettable ones. The deep field photographs filled with galaxies like scattered jewels on velvet. But even Hubble had its limits. It could peer back to redshift 6 or 7 with effort, giving us glimpses of galaxies from when the universe was around 1 billion years old. And though those galaxies were young, they were still expected to be chaotic, full of clumps and swirls and the turbulent drama of birth. Scientists expected that if we could look back even further, we would find something messier still. The early universe was believed to be a place of raw ingredients, clouds of hydrogen and helium slowly condensing under gravity, igniting into stars, forming the first galaxies, small, irregular, dim. It would be a patchwork of cosmic adolescence, a turbulent teenage phase of the cosmos. Webb was meant to be our window into that awkward, chaotic past. The telescope itself is a marvel. Its mirror is 6.5 metres wide, composed of 18 hexagonal segments coated in gold to optimise infrared reflectivity. Its instruments are kept colder than the coldest places in the solar system, just a few dozen degrees above absolute zero, because to see the faint heat signatures of the earliest galaxies, the telescope must itself emit as little heat as possible. It's parked 1 million miles away from Earth at a point called L2, a gravitationally stable place where it can keep its back to the sun and face the darkness uninterrupted. When Webb opened its golden petals and began observing, scientists held their breath. Years of engineering, budget crises, delays, and careful alignments had led to this moment. They pointed it at patches of seemingly empty sky, the same trick Hubble had used to such great effect, and waited for the photons, the ancient light, to arrive. What they expected to see was a universe still stumbling out of its infancy. Faint glimmers of tiny galaxies struggling to organise themselves, stars just beginning to form, dust clouds tangled and turbulent. The story was supposed to unfold like a slow burn. Gravity pulling things together, hydrogen igniting, structure forming gradually over billions of years. But what came back was not what anyone had expected. There were galaxies, many of them, but they weren't small, they weren't faint, they weren't disorganised. They looked mature, structured. Some were shaped like discs, flat and graceful. Some had distinct bulges, cores, even signs of rotation. These were not cosmic infants. They were galaxies that, by our understanding, simply had no right to exist so early in the universe's timeline. And they weren't rare. There were more of them than anticipated, and they were brighter and heavier. It was as if someone had flipped a few pages ahead in the cosmic story and forgotten to tell the rest of the class. The early universe was not just forming galaxies, it was filled with them, and they seemed to have skipped entire chapters of development. At first, researchers were cautious. Maybe these galaxies weren't as far away as they seemed. Maybe the redshifts had been overestimated. Maybe the mass calculations were off. Maybe something in the modelling was skewing the data. But as more observations came in, the pattern held. These galaxies were there. They were early, and they were wrong, at least by the standards we had built our universe upon. The James Webb Space Telescope, this quiet observer of ancient light, had gently pulled a thread from the fabric of cosmic understanding. And the stitch it opened was not a tear, but an invitation, a beckoning into something stranger, older, and more beautiful than we had imagined. There's a quiet thrill that runs through the scientific community when a mystery arrives, uninvited but undeniable. Not a loud, chaotic puzzle, but a soft contradiction, a presence that shouldn't exist, calmly sitting where absence was expected. That's how it began with the first full images from the James Webb Space Telescope. The early data revealed something far more provocative than anticipated. Galaxies that did not wait their turn. Galaxies that appeared fully formed in an era when we expected only beginnings. Galaxies that came too soon. The redshifts of these galaxies, some measured at Z, equals 10, 12, even approaching 16, placed them within the first 300 to 400 million years after the Big Bang. In cosmological terms, this is barely a blink, a cosmic heartbeat after the supposed beginning. And yet, there they were, not faint wisps of barely assembled matter, but brilliant structures with mass, shape, and surprisingly high levels of complexity. Some had spiral arms, others appeared as rotating disks. Several contained central bulges dense with stars, features typically associated with much older galaxies, and most confounding of all, many exhibited signs of chemical enrichment. These weren't primordial clouds, they were made of stars that had already lived, died, and given birth again. To find that level of maturity so early was like discovering a child reciting poetry before learning to speak. In particular, astronomers noted high metallicity in some of these galaxies. In astrophysical language, metals are all elements heavier than hydrogen and helium. They are forged in the hearts of stars and spread by supernovae. So for a galaxy to be metal-rich, it must have already gone through multiple generations of stars. That kind of recycling takes time, or so we thought. Yet these galaxies, at the far edge of observability, were already seasoned with the fingerprints of stellar history. This raises a question that echoes more deeply than it seems. How much time is enough for something to become complex? And what if our measurements of time itself are part of the illusion? In the standard cosmological model, Lambda cold dark matter, galaxies are thought to grow hierarchically. Small clumps of matter merge over time, building up larger structures. It's a slow, often violent process, governed by dark matter scaffolding and the gradual cooling of gas into stars. The early universe, then, should have been a place of incompleteness, lumpy, irregular, full of cosmic construction zones. But the galaxies seen by Webb appear, in many cases, to have skipped those early steps. They resemble not scaffolds under assembly, but cathedrals already glowing with candlelight. It's not just their presence that's puzzling, it's their polish. And so, astronomers and physicists began the careful, uncomfortable process of questioning. Was it possible the measurements were off? Could redshifts have been misinterpreted? Was there some exotic dust skewing the readings? Could these galaxies be closer and therefore younger than they seemed? Instruments were rechecked, models were revised, but the trend persisted. If the measurements hold, and they seem increasingly likely to, then something fundamental is amiss. Either galaxies formed far faster than our current understanding of physics allows, or our assumptions about the early universe, about time, structure, and how the cosmos builds itself, are in need of re-evaluation. To grasp the scope of this issue, imagine that you expected to find a sapling growing in a recently cleared field, and instead discovered a towering oak, its roots deep, its branches wide, its bark already etched by decades of wind. The discovery doesn't just alter your understanding of the tree, it changes how you think about the entire timeline of the forest. One particularly striking example from the JWST data was a candidate galaxy called CEERS-93316, initially measured at a redshift of nearly 17. Though later recalibrated slightly lower, it hinted at the possibility of galaxies existing just 200 million years after the Big Bang. At that point in cosmic history, the universe was still undergoing reionization, a process where early light from the first stars and galaxies began reionizing the neutral hydrogen that had filled space since recombination. It was a turbulent era, expected to be sparsely populated, but CEERS-93316 and others like it suggested otherwise. And then came the black holes. Even more surprising than the galaxies were the compact objects discovered at their centres. Supermassive black holes, millions or even billions of times the mass of our Sun, were detected in galaxies that existed when the universe was less than 1 billion years old. According to our best estimates, it takes hundreds of millions of years under the most favourable conditions for black holes to grow that large. But here they were, already formed, already active, already anchoring galaxies that weren't supposed to exist yet. Their presence forces an uncomfortable rethinking. Either black holes grow faster than we understand, possibly through unknown mechanisms, or they formed differently altogether. Perhaps some theorized primordial black holes could have emerged from density fluctuations shortly after the Big Bang, seeding galaxies rather than arising within them. It's an inversion of causality that's hard to wrap one's mind around. We tend to think in sequences. First clouds form, then stars ignite, then black holes emerge from stellar collapse. But if black holes came first, if they somehow shaped the galaxies around them, then we may have been narrating the cosmic story in reverse. In the midst of this scientific quiet storm, one thing became clear. The universe, our universe, had matured too quickly. Like finding grandparents in the nursery, it challenged not just our models, but our expectations, our metaphors, and the comforting notion of a universe that unfolds slowly, predictably, with time as its dependable guide. Instead, what Webb revealed was a cosmos that had already written full paragraphs where we thought we'd find only scribbles. A cosmos that whispered, gently but firmly, "You may need to start the story again, not from the beginning, but from somewhere else entirely." The further we look into space, the further we see into time. And the further into time we peer, the more fragile our models become. They stretch, bend, and eventually begin to fray at their edges. What the James Webb Space Telescope offered, beyond its luminous images and scientific precision, was a quiet, almost poetic reminder. The past is not always what we imagined it to be. In the earliest light ever captured, something didn't line up. The galaxies came too soon, that much was clear. But the deeper shock arrived in what those galaxies contained. Stars too old for their surroundings, and black holes too massive for their age. Let's begin with the stars. When we speak of the first stars, we refer to what astronomers call population 3 stars. These would have been the earliest generation of stars to form, composed almost entirely of hydrogen and helium, the lightest, most abundant elements forged in the Big Bang's aftermath. Heavier elements like carbon, oxygen, iron and gold didn't yet exist. They would be formed later, in the fiery furnaces of stars themselves, scattered by supernovae into the interstellar medium. These early population 3 stars are expected to have been massive, hot and short-lived. They burned bright and fast, creating the first heavy elements, or metals, as astronomers call them. Only after several cycles of stellar birth and death would the universe become chemically enriched enough to form the kinds of stars we see today. Population 1 and 2 stars, with varying amounts of metals in their makeup. The timeline for all this, according to our models, is not quick. It requires the universe to form stars, then wait as those stars die, then mix their ashes into new clouds of gas and begin again. Yet, in the galaxies revealed by JWST, astronomers observed signs of unexpectedly high metallicity. Stars whose light indicated they had already been born into environments rich in heavier elements. This implies that earlier generations of stars had already lived and died, perhaps more than once, within just a few 100 million years of the Big Bang. To put it gently, this is problematic. Chemical enrichment takes time, and time was supposed to be in short supply. What JWST seemed to show was a universe that had already matured, that had not only built galaxies but had filled them with generations of stars and the chemical complexity that comes from stellar recycling. These weren't primordial structures, they were more like old neighbourhoods, weathered and well-lived, where the houses have been rebuilt more than once. But even that wasn't the most unsettling part, because nestled at the heart of some of these ancient-looking galaxies were objects far heavier than any expected to be there. Black holes millions or even billions of times the mass of our Sun. These were not the small stellar mass black holes left behind when massive stars explode. These were supermassive black holes, the kinds that today sit quietly at the centres of galaxies like the Milky Way, influencing the orbits of billions of stars, shaping the dynamics of entire galactic cores. And yet, JWST saw signs of them already formed and active when the universe was still in its infancy. In some galaxies, the light was so bright in the centre that it suggested an accreting black hole, a quasar, feeding on gas and dust, heating its surroundings to the point of radiance. The puzzle isn't just that these black holes existed, but that they had apparently grown so massive so quickly. Even under the most generous assumptions, rapid accretion, no interruptions, no feedback limiting growth. It's difficult to explain how they reach such enormous sizes in so little time. To visualise the scale of the problem, imagine you planted a seed this morning, and by nightfall you found a towering tree with thick bark, wide branches and deep roots already disturbing the pavement. Something is off. Either the tree didn't grow in the way you assumed, or it didn't start from a seed, or perhaps it had always been there, waiting just beyond your notice. One potential solution, though still theoretical, is the idea of primordial black holes. These would have formed not from collapsing stars but from dense regions of space itself, early in the universe's history, perhaps within the first second after the Big Bang. If such black holes existed, they might have served as seeds around which galaxies formed, rather than being their byproducts. In this inverted view of cosmology, black holes are not the endpoints of stellar death, but the starting points of cosmic structure. It's a reversal that changes everything. But primordial black holes remain speculative. No conclusive evidence has been found, and even if they did exist, they raise more questions than they answer. What caused their formation? Why did they vary in mass? Why are they still so massive? Why didn't they evaporate due to Hawking radiation? Other possibilities include exotic physics, changes to the behaviour of gravity under extreme conditions, or undiscovered mechanisms that allow black holes to grow more efficiently in the early universe. But every adjustment made to the model to account for these observations creates ripples elsewhere, affecting how we understand dark matter, structure formation, the cosmic microwave background, even inflation. Like pulling a thread in a finely woven tapestry, it's difficult to predict which parts will unravel. And so, faced with stars too mature and black holes too massive, the scientific community finds itself in an unusual position, not denying the observations but carefully reopening the assumptions that gave rise to them. The universe hasn't contradicted itself, it's only contradicted our expectations, and there's a quiet wisdom in that. Perhaps we expected too much simplicity from something as old and vast as the cosmos. Perhaps our ideas about early and late, before and after, were shaped too tightly by the way we experience time here on Earth. A narrow window of days and seasons and lifespans. The universe doesn't think in hours or years or epochs. It simply unfolds in whatever sequence reality allows. James Webb didn't break the universe. It only showed us where our stories need revising. If you've ever watched the sun set and noticed how the light shifts, from bright gold to dusky orange, then to the softest red, you've seen what happens when light stretches. It's a quiet, familiar moment, the kind we don't usually associate with cosmic truths. But in that gentle fading is the same principle that guides our understanding of the universe's deepest past. Redshift, the lengthening of light's wavelength as it travels through space, is not just an astronomical measurement. It's our primary clock, our ruler, our storybook of time. And like all stories, it may be more poetic than precise. Redshift is often introduced as a kind of Doppler effect. Just as the sound of a passing train drops in pitch as it moves away, the waves stretching out behind it, light too stretches when its source moves away. This is how we know that distant galaxies are receding from us. The universe is expanding, and the light from those galaxies is being drawn out, thinned, cooled into redder and redder wavelengths by the fabric of space itself. But in cosmology, redshift is treated as more than motion. It's a proxy for time. The farther a galaxy is, the more redshifted its light becomes, and the older that light is. In effect, to look at something with a redshift of, say, 10, is to look at it as it was when the universe was only a few 100 million years old. We call this look-back time, and we use it to reconstruct the sequence of cosmic events, the rise of the first stars, the growth of galaxies, the formation of structure. Yet here is where things begin to ripple. Because redshift is not time itself. It is the stretching of light, not the ticking of a clock. The translation from redshift to age is not measured directly. It is inferred through models, mathematical frameworks that describe how the universe expands over time. And those models, while precise and powerful, rely on assumptions about the density of matter and energy, about the rate of cosmic expansion, about what space itself is and how it behaves over unimaginable distances. If those assumptions shift, even slightly, then the entire translation begins to tilt. A redshift of 12 might no longer mean 350 million years after the Big Bang. Bang! It might mean something else entirely. Or, more unsettlingly, it might mean that the concept of after itself begins to dissolve. Let's imagine for a moment a thought experiment. Picture a map. not of space, but of a journey you took as a child. On this map, you've drawn where the hills were steep, where the river bent, where the house on the corner had the blue roof. Years later, you look at that map and begin to reconstruct the route. But something feels off. The hill seems too steep for the distance covered. The river turns before the bend in the path. The sequence begins to blur, and you realise that perhaps your memory of the route was never about time or distance, but about feeling. Sequence became story, and story doesn't always follow rules. In a similar way, our use of redshift assumes a straightforward relationship between distance, expansion, and time. But what if the early universe expanded differently than we thought? What if time itself did not flow at a constant rate, especially near the earliest moments of the cosmos? What if early and late are terms that make sense only from our current position, like judging a movie's pacing from its final scene? This becomes especially relevant when we consider that most redshift to time conversions are built into the Lambda CDM model, the standard model of cosmology. It assumes a particular blend of dark energy, dark matter, and baryonic matter. It assumes a particular rate of expansion, and it applies these assumptions to interpret every redshift measurement we make. But if the James Webb Space Telescope is revealing galaxies that seem too developed, too structured, too massive for their redshift, then we may not be looking at a failure of observation. We may be looking at a failure of interpretation. Some cosmologists have begun to suggest that we need a new way of reading the redshift record, not discarding it, but decoding it differently. Perhaps redshift includes information not just about velocity and distance, but about the changing nature of time itself. Maybe the early universe unfolded in a nonlinear rhythm, expanding quickly at first, then slowing, or pulsing in waves. Maybe time at the beginning was not like time now. Maybe it didn't flow at all. Maybe it crystallized. Quantum gravity theorists often speak of time as emergent, not something that exists independently, but something that arises from relationships. In this view, time is not a thread stretched through space, but a shadow cast by changes in systems, a measure of before and after, only made possible by interactions. In the earliest universe, when those interactions were rare, maybe time hadn't quite switched on yet. Or maybe it was coiled in dimensions we don't yet understand. And so we come back to redshift, not to discard it, but to regard it with a little more wonder. It is still our window into the past, but like a stained glass window, it may also colour what we see. The galaxies James Webb has found are not mistakes, they are messengers. And the message may be this: the order in which we think the universe unfolded might not be the order it lived. It's possible we've been reading the timeline like a straight line, neat and progressing, when it may actually resemble a spiral or a quilt, or something we haven't yet imagined. And if that's true, then redshift is not just a measurement, it's a key, not to the past we thought we'd find, but to a new way of thinking about what past even means. Every great scientific theory begins as a question, grows into a framework, and eventually becomes a kind of map. One we rely on so deeply that we sometimes forget it was drawn by human hands. For over 2 decades, the Lambda CDM model has been that map. L, for the cosmological constant, representing dark energy, the invisible force pushing the universe apart, and CDM for cold dark matter, the unseen scaffolding around which galaxies form and cluster. Together, these components created a model so effective, so elegant, and so predictive that it has been called the standard model of cosmology. But even the most beautifully drawn maps can begin to feel the tremors of shifting ground beneath them. To understand Lambda CDM is to appreciate its quiet brilliance. It emerged not from a single discovery, but from a slow, careful synthesis of many. The cosmic microwave background, a faint afterglow from the early universe, provided a baby picture of everything. Its minute fluctuations rippling across space were modelled with remarkable accuracy by Lambda CDM. The large-scale structure of galaxies, observed in sweeping surveys across the sky, matched the patterns the model predicted. And even the expansion of the universe, accelerating faster than expected, found an elegant placeholder in the form of lambda, Einstein's long discarded but now resurrected cosmological constant. This model told a coherent story. In the beginning, a hot, dense state, then rapid expansion, cooling, and the slow formation of structure. Gravity gathered dark matter into halos. Gas settled into these invisible wells, cooled, and ignited into stars. Galaxies grew, collided, and evolved. Over time, dark energy took over, driving galaxies apart at ever-quickening speeds. And here we are, looking back through it all, mapping each moment through redshift, light, and theory. But even the best stories begin to show seams, and the seams of Lambda CDM have been growing more visible. The first major crack was the so-called Hubble tension, the persistent and growing discrepancy between two ways of measuring the universe's expansion rate. When we observe the early universe, particularly the CMB, and extrapolate forward using Lambda CDM, we get a value for the Hubble constant, the rate at which space is stretching. But when we measure the expansion rate of the nearby universe directly, using supernovae and other distance markers, we get a faster value. The two don't agree, and no amount of improved measurement seems to be closing the gap. If anything, it's widening. At first, this was chalked up to calibration errors, the kind of statistical noise that fades with better instruments. But as data from both early and late universe measurements improved, the gap remained stubborn. It became less a quirk and more a whisper. Something might be missing. And then came the James Webb Space Telescope. As we saw earlier, JWST didn't just peer deeper. It saw galaxies that seemed too grown, too bright, too structured for the timeframes predicted by LCDM. According to the model, the early universe was too young for such maturity. The processes of cooling, collapsing, igniting, enriching and assembling should have taken longer, but the galaxies didn't wait. And neither did the black holes. They were already there, formed, luminous, commanding. Like discovering a novel that begins not with a blank page, but with characters already halfway through their arcs. Each of these anomalies, on its own, could be dismissed. Perhaps a misinterpretation, a glitch, an outlier. But together they begin to form a quiet chorus. Not a scream, not a crash. Just the steady hum of something out of tune. Now to be clear, Lambda CDM is not collapsing in the way failed theories do. It still predicts the behaviour of the cosmic microwave background with stunning precision. It still models the growth of structure across billions of light years. It still explains most of what we see, most of the time. But in its elegance, it may have left out something essential, something subtle. And that subtlety may be the gap where our understanding falters. Some scientists advocate for refinement, not revolution. They suggest tweaking parameters, introducing new particles, modifying the properties of dark energy, or adjusting the initial conditions of the universe. Perhaps the tension can be resolved with the right adjustments. Perhaps the anomalies are clues to extensions, not replacements. Others, more cautiously, wonder if we've reached the edge of what Lambda CDM can contain. Like an old house that's still beautiful but no longer fits the lives lived within it. We don't demolish the house, we honour it. We remember why we built it, and we begin to ask what might come next. Part of the challenge is that Lambda CDM rests on foundations we still don't fully understand. Dark matter, the CDM in the name, has never been directly detected. We infer its presence from gravitational effects, but we've never seen a particle of it. Dark energy, the lambda, is even more mysterious. We know it's driving acceleration. We don't know what it is. We name it with a letter. But the truth is, it's a placeholder for something we don't yet grasp. And so, the standard model of cosmology finds itself in a tender place. Still useful, still luminous, still better than anything else we've built. But under strain. It's like a great ship that carried us across a vast ocean and now trembles slightly as it reaches unfamiliar shores. No one wants to abandon the ship, but more and more, people are peering over the edge wondering what's beneath the surface, and what kind of vessel we'll need for the journey ahead. Imagine trying to watch a tree grow, not over years or decades, but in the span of an hour. You plant the seed, close your eyes briefly, and when you open them again, you find not a sprout or a sapling, but a towering oak. Roots split through the pavement, branches touching the clouds. That, in essence, is the unease creeping through cosmology right now. The James Webb Space Telescope has allowed us to glimpse the universe's youngest epochs, and what we're seeing are structures, galaxies, stars, black holes, that appear far too mature for the amount of time the universe is supposed to have given them. Something doesn't add up. Either the universe learned to build faster than we thought possible, or our idea of how time works is in need of a quiet, radical rethinking. Let's begin with what's expected. In the standard picture of cosmic evolution, time is like a stage. First comes the Big Bang, then a brief period of inflation, where space stretches at incomprehensible speed. After that, the universe cools, the first atoms form, and light is finally free to travel. Then gravity begins its patient work, pulling gas into clouds, triggering the first stars, seeding galaxies, and over billions of years, constructing the grand architecture we now observe across the sky. All of these processes take time, not just in the human sense, but in a thermodynamic, gravitational chemical way. Gas clouds need to cool before collapsing. Stars take millions of years to form, live, and die, enriching their surroundings with heavier elements. Black holes grow slowly, feeding on gas and stars, their mass increasing over cosmic epochs. Feedback loops from supernovae and active galactic nuclei regulate this process, creating bursts and pauses in the rhythm of cosmic construction. But the galaxies J-Digestic has revealed seem to disregard this pacing. They're not struggling into existence. They're not early drafts. They're finished, or at least far more developed than expected. Some are massive, with stars already showing signs of advanced chemical evolution. Others are too bright, too organized, and at the heart of several, as we've seen, lie black holes whose masses imply a history of sustained, rapid growth that simply doesn't fit within the timeline available. This is what we mean by a compressed timeline. The script, as written, doesn't allow for these scenes to occur so early. The actors are showing up in the wrong act, fully in costume, already deep into their roles. For the standard model to accommodate this, something fundamental would need to speed up, not just by a little, but by orders of magnitude. One might try to salvage this by proposing that the first stars and galaxies formed far more efficiently than we thought, that the cooling of gas, the formation of structures, and the birth of black holes happened under extraordinary conditions we've yet to fully model. It's possible, but it's also deeply unsatisfying, because every tweak we make to accelerate formation introduces new tensions elsewhere. In the observed distribution of galaxies, the uniformity of the cosmic microwave background, the elemental abundances produced in the first few minutes after the Big Bang. Another option is to modify the physics, to suggest that gravity behaved differently in the early universe, or that exotic particles played a role in catalyzing structure. Again, these ideas are not impossible, but they require rewriting parts of the model that have otherwise worked remarkably well. And when you start adjusting the rules mid-story, it becomes hard to tell whether the story still makes sense at all. So a third, quieter idea begins to surface, not as a certainty, but as a possibility we might need to entertain. What if the problem isn't with the structures we see, but with our understanding of time itself? It's an idea both thrilling and disorienting. Time, after all, is the most fundamental backdrop we have. Everything we know unfolds within it. And yet, in physics, particularly in the realms of quantum mechanics and general relativity, time is slippery. It flows differently depending on your position, your speed, your mass. It bends near black holes. It can dilate, stretch, and loop. And in some theories of quantum gravity, time doesn't exist as a primary ingredient at all. It emerges from correlations between events, from changes, from relationships, not from an underlying clock. If that's the case, then perhaps what we're interpreting as a compressed timeline is not a problem of speed or growth, but a sign that our calendar is wrong, that we've been mapping sequences onto something that doesn't unfold linearly. That redshift may not correspond cleanly to age, or at least not in the straightforward way we've assumed. Maybe time, near the origin of the universe, wasn't what we think of as time. Maybe it was thicker, or looser, or still forming. Perhaps the early universe didn't experience time in a steady stream, but in pulses, moments of rapid change followed by long plateaus. Or perhaps time is like space, capable of warping in ways we don't yet comprehend. If that's true, then our models, built on the assumption of a smooth, continuous ticking, would be projecting an illusion, a version of history that feels coherent but isn't quite real. It's worth noting that these ideas aren't speculative nonsense. They come from the edges of well-developed theories. Loop quantum gravity, causal set theory, and certain interpretations of the holographic principle all suggest that time might be emergent, approximate, or contextual. In such a framework, what looks like a paradox from within the model might be resolved when we step outside and realize that the model itself has edges. And so we return to the galaxies, not as errors but as revelations. They are not just distant specks of light. They are signposts pointing us towards something deeper. Perhaps they're telling us that the universe doesn't follow our clock, that it never did, that our sense of what comes first, what takes time, what must happen before something else, all of it may be a human construction, useful, beautiful, but incomplete. And if that's true, then the impossible timelines we're seeing are not flaws in the cosmos. They are flaws in our expectations, and in their quiet contradiction, they invite us to reconsider not just when the universe began, but how we think beginnings even work. From the time we are children, we learn to ask a certain kind of question. When did it start? We want origin stories. For people, for places, for everything. We like things to begin. The first day of school, the first page of a book, the first heartbeat. The idea of a beginning comforts us. It gives structure. It provides a boundary to the story. Without one, we feel adrift, as if we've stepped into a tale already underway with no prologue, no title, no sense of how to place ourselves in the unfolding. But what if the universe never began? What if that comforting edge, the line we imagine separating nothing from something, simply isn't there? This is not a new idea. Philosophers, mystics and physicists have all, in different ways, circled around it for centuries. But now, with the observational anomalies piling up, galaxies that seem too developed, black holes too massive, timelines too compressed, the question is beginning to feel not just poetic, but scientific. What if the reason we can't find the start of everything is that there wasn't one? The Big Bang theory, as commonly understood, does not actually describe a bang in the way we picture explosions. It is a model of expansion, a mathematical framework describing how space itself stretches over time. It tells us that the universe was once hotter, denser, and smaller. It gives us a stunningly accurate prediction of the cosmic microwave background. It explains the relative abundances of hydrogen, helium, and lithium. But it does not tell us where the universe came from. It begins from a state of very hot and dense, and works forward. The moment before, that remains undefined. When we trace time backward using general relativity, we reach a singularity, a point where the equations break down, where density and temperature become infinite, and space-time curvature becomes unmanageable. But many physicists believe this singularity isn't real. It's a signpost that our current theories are incomplete. General relativity, after all, does not include quantum effects, and near the supposed beginning, quantum gravity must dominate. This opens the door to other possibilities, models in which the universe did not begin but transitioned. Cyclical models, eternal inflation. Quantum cosmologies where time as we know it is not a pre-existing backdrop but a product of entangled states. Take the idea of the Big Bounce, for instance, a cosmology in which the universe did not emerge from nothing, but rebounded from a prior contraction. Like a ball hitting the ground and rising again, the bounce replaces the singularity. In this model, our universe is one phase in a potentially infinite sequence of expansions and contractions. There was never a first cycle, just as there is no last. Or consider the no-boundary proposal, developed by Stephen Hawking and James Hartley. In this model, time near the origin becomes space-like, a direction you can move through, but not one that implies before and after. The universe, in this view, is finite but unbounded. Like the surface of a sphere, it has no edge, no starting point, no boundary where things begin or end. There simply is. Another candidate, Conformal cyclic cosmology, proposed by Roger Penrose. Here, time is infinite in both directions, but the distant future of one universe becomes, through a kind of conformal transformation, the beginning of the next. In this view, aeons succeed one another, each one birthing a new cosmos, not from a fiery blast, but from the cooled-out, stretched remains of the previous one. There's no sharp break, just a soft fading into reformation. All of these models share something in common. They remove the need for a hard beginning, and by doing so, they invite us to question our deep attachment to starts, origins, and edges. Why are we so insistent that there had to be a moment of creation? Part of it is cultural. Many of our stories, religious or scientific, are built around Genesis, but part of it is neurological. We experience time in a particular way. Our memories form a line. Our lives have a clear start, birth, and an eventual end. We are creatures of sequence, and so we project sequence onto everything. But the universe may not share that tendency. If time is emergent, a product of relationships, of change, of measurement, then it may not have existed at the beginning. Or what we call the beginning may not be a point, but a region, a condition, a transition from timelessness to timefulness. In quantum cosmology, the wave function of the universe contains all possible histories. From our perspective, only one unfolds, the one we observe. But from the perspective of the whole, time may be just a coordinate, not a necessity. Like choosing a direction to walk on a landscape, rather than a track you're forced to follow. So when we see galaxies appearing too soon, or black holes, already massive before time allowed, we might be seeing the footprints of a universe that did not emerge but always was. A cosmos that didn't begin but unfolded, not from nothingness, but from something outside our language, our logic, and perhaps our comprehension. And instead of resisting that mystery, maybe we can begin to relax into it. Maybe beginnings are only real from within a system. From outside there is only presence, only becoming, only the ever-shifting now. The question isn't what came before the universe. It might be, what made before a meaningful word in the first place? It's easy to imagine beginnings as hard edges, a match strike, a curtain lifting, a thunderclap that breaks the silence. That's how the Big Bang has long been pictured. A singular event, dense and hot beyond comprehension, igniting the universe from nothing. But nature, more often than not, prefers continuity to rupture. Rivers don't start from a single drop. Forests don't rise overnight. And maybe, just maybe, the universe didn't begin at all, it turned, like a tide changing direction, like a breath being drawn in after being let out. This is the core idea behind the Big Bounce. The Big Bounce is more than a poetic inversion of the Big Bang. It emerges from one of the most promising areas of theoretical physics, loop quantum cosmology, or LQC. At its heart lies a simple, radical question. What if the singularity, that infinitely dense point we claim mark the birth of the universe, isn't real at all? What if, instead, it's a mirage created by our incomplete understanding of gravity and quantum mechanics? General relativity, powerful as it is, cannot describe what happens at extreme densities. It breaks down at the Planck scale, where distances and energies approach the limits of measurement itself. Here, quantum effects become dominant, and space and time, which we treat as smooth and continuous, may reveal a deeper granular structure. That's where loop quantum gravity steps in. Developed by Abhay Ashtekar, Martin Bodgerwald and others, loop quantum gravity proposes that space is not continuous, but made of tiny discrete units, loops woven together, forming a quantum fabric. These loops are unimaginably small, on the order of the Planck length, about 10 to the negative 35th meters. But their collective behaviour could change everything we thought we knew about the universe's earliest moments. In this framework, gravity doesn't just pull, it repels under certain extreme conditions. As a universe contracts toward what would traditionally be a singularity, this repulsive quantum gravitational force kicks in, preventing complete collapse. Instead of ending in a point of infinite density, the universe rebounds. It bounces. What lies on the other side of the bounce is speculative, but mathematically it may be another universe, one that contracted before expanding into our own. In this view, our Big Bang wasn't the beginning of everything. It was the beginning of this phase, a transition, not a creation. Think of it like compressing a spring. You press, and just when the tension becomes unbearable, it snaps back, expanding outward. That moment of rebound is what we see as the Big Bang, but the energy, the fabric, the potential, all of it had been accumulating through a prior cycle. A cycle we'll never directly observe, perhaps, but one whose echo we carry in the structure of our cosmos. Loop quantum cosmology doesn't just remove the singularity, it gives us continuity, a universe that is, in some deep sense, eternal. No beginning, no first moment, just an infinite rhythm of contraction and expansion, each phase resetting the conditions, each bounce marking a handoff from one cosmic breath to the next. This kind of model is appealing not only because it removes infinities, which physicists generally view with suspicion, but because it preserves the laws of physics in a more complete way. Singularities, after all, are places where the laws break down. They are the mathematical equivalent of we don't know, but in LQC the laws evolve smoothly through the bounce. There is no moment of failure, no rupture, just a gentle reversal of direction. Ashtekar has called this a new paradigm for the beginning of the universe. Not a singular moment of magic, but a quantum transition, governed by physics, describable by mathematics, unfolding through time, even as it reshapes our understanding of what time is. And while we cannot observe the pre-bounce universe directly, the expansion erases much of that memory. Its influence may linger. In principle, certain features of our universe's structure, or subtle imprints in the cosmic microwave background, could carry the signature of a bounce rather than a bang. These are questions future missions may explore, but already the conceptual shift is powerful. Because once you accept that the Big Bang may have been a bounce, other assumptions begin to soften. You stop imagining the universe as a one-way street, heading outward from a mysterious origin. Instead, you begin to picture something cyclical, flowing, pulsing with creation and destruction, collapse and renewal. Not metaphorically, but literally. The very structure of reality breathing in and out. It's tempting to ask, what caused the previous universe to contract? But perhaps that's the wrong question. In a cyclical cosmos, no single moment needs a cause. There is only transformation. Just as spring follows winter and winter follows fall, the bounce may be part of a larger timeless pattern. And if that's the case, then the universe did not begin in chaos. It emerged from memory, a memory of form folded back on itself, a memory we call expansion, but which may be in the deepest sense a continuation. This doesn't answer every question. Loop. Quantum cosmology is still in development and its predictions remain difficult to test. But its beauty lies in what it offers. Not a theory of everything, but a gentler starting point. A cosmos without rupture. A timeline without a start. A rhythm that may go on forever, one bounce at a time. Imagine standing at the shore just before dawn. The ocean stretches out in front of you, still and immense, the horizon blurred by mist. You cannot see what came before the waves you now hear, only that they've been travelling a long time. One after another they arrive, break, and vanish. But somewhere out there, far beyond your sight, something began them. Or perhaps nothing began them at all. Perhaps the waves are part of an unbroken rhythm. No first wave, no last. Only motion, only echo. This is the kind of vision that inspired physicist Roger Penrose's idea of conformal cyclic cosmology, a model in which the universe has no real beginning and no final end, only a succession of aeons, entire universes, each arising from the slow, stretched-out death of the one before. Each aeon ends not in fire, but in silence, and from that silence, a new cosmos emerges. At first, this idea seems to defy common sense. How can one universe give rise to another without starting over? Doesn't entropy, the slow drift toward disorder, make this impossible? In traditional thermodynamics, high entropy states can't become low entropy states without input. But Penrose's model sidesteps this by reframing what we mean by entropy at the far ends of time. In conformal cyclic cosmology, the end of a universe is not a cold, lifeless scattering of matter, but a transformation. As time stretches forward, trillions upon trillions of years, black holes slowly evaporate through Hawking radiation, galaxies drift apart, stars die out, and matter thins. What remains is energy, a thin sea of radiation. Mass loses meaning. Temperature gradients fade. Eventually, even time itself becomes less meaningful because there are no longer any processes to measure it by. In that utterly smooth, scale-free future, something strange happens. The physics of the universe becomes conformally invariant. Conformal symmetry is a kind of mathematical behaviour in which the shape of things matters more than their size. If mass no longer matters, if everything that remains is radiation, light and geometry, then the universe's final state can, in a very specific mathematical sense, be squashed into something that resembles the beginning of a new universe. The infinitely stretched future becomes the compressed seed of the next. It's like turning the hourglass over, not because time reversed, but because the shape of the sand at the bottom becomes the shape of the top once again. Each of these transitions, from one aeon to the next, leaves no physical border. There is no wall, no bang, no rupture, just the smooth handing off of geometric conditions, a whisper passed forward, not a shout. Our universe, in this view, is simply one in a series, not the first, not the last, just one breath in a long eternal rhythm, and perhaps, if we're quiet enough, we can still hear the echoes. In 2010, Penrose, along with physicist Vahey Ghazardian, made a bold claim. They had found evidence for this theory in the cosmic microwave background. Specifically, they reported the presence of concentric low-variance circles, subtle ripples of temperature that, they suggested, could be the imprints of black hole collisions from the previous aeon. The idea was not universally accepted. Many in the cosmology community remained sceptical, citing the need for more robust statistical validation. But the claim did something arguably more important than confirm a theory. It gave the scientific community a reason to look, to ask, if our universe carries the fingerprints of a life before, where would they be? What would they look like? What kind of light could travel across not just space, but across cosmic lifetimes? The poetic beauty of CCC is that it allows for memory, not just as metaphor, but as a physical trace. Each universe becomes the ancestor of the next, not by storytelling, but by geometry. And just as we carry remnants of stars in our blood, perhaps the universe carries remnants of its predecessors in the patterns of its earliest light. Philosophically, CCC invites us to think of the cosmos not as a single story, but as a library. Each aeon is a volume. Each volume ends quietly and fades, but in doing so, it lays the foundation for the next. The past is not erased. It is transmuted. It becomes structure, not content. This changes how we might feel about beginnings. We're used to thinking of origins as clean starts. The first line in the book, the 0 on the clock. But in a cyclical model like 300, there are no blank pages. The story always begins mid-sentence, because it has never truly stopped. The edges blur, the old becomes the new, and the new in time becomes old again. This model doesn't eliminate mystery. In many ways, it deepens it. We still do not know why the cycles occur, what governs their passage, or how many eons have come before. But it softens the boundaries. It invites us to imagine a universe not bounded by nothingness, but by transformation. Not sparked into being, but eased into continuity. And perhaps that's the gentlest kind of creation, one without rupture, one without panic or suddenness. A turning of a page you didn't realise had already begun to flip. So if you look up at the night sky and wonder where it all began, perhaps the answer isn't back there, or before this. Perhaps it's again, and again, and again. Some ideas arrive not like a thunderclap, but like fog at dawn. Quiet, inevitable, softening the edges of what you thought you knew. One of those ideas came from Stephen, Hawking and James Hartley, who asked, what if the universe didn't start with a bang at all? Not even a bounce or a birth, but with a gentle rounding so smooth that the word beginning no longer really applies. This was the essence of their no-boundary proposal. Not just a shift in cosmological modelling, but in the way we picture the origin of time itself. And it began with a deceptively simple analogy, one that gently rewrites the rules of how we think about beginnings. Picture the Earth, more specifically the South Pole, not the icy outpost itself, but the conceptual idea of it. A location on a globe where all longitudinal lines converge, where compass directions lose meaning, and where, despite that convergence, there is no edge. You don't fall off the Earth at the South Pole. You don't find a sign that says here ends the planet. It's just a rounded bottom, smooth, finite, but without a boundary. There's nowhere further south to go. And yet, there's nothing abrupt about it either. Hawking and Hartle wondered, what if the beginning of the universe were like that? In standard cosmology, we run the equations of general relativity backwards and arrive at a singularity, a point of infinite density and temperature, where the rules of physics break down. But they saw something else. They imagined that, near this so-called beginning, time might not behave the way we experience it now. Instead, time might become space-like, another dimension of space, curled up, smooth, and without direction. This concept is difficult to picture. Our experience of time is so deeply linear that even imagining it turning sideways feels disorienting. But mathematically, in the framework of quantum cosmology, this transformation makes sense. Near what we would call t equals 0, time ceases to be a ticking axis and becomes more like a direction within space, something without before or after. A curved surface instead of a timeline, a soft rise instead of a hard beginning. Their equations describe the universe as a Euclidean manifold, 4 spatial dimensions with no time, transitioning into the Lorentzian manifold we inhabit, where time becomes distinct. In other words, the universe starts as a purely spatial object and then, through quantum processes, evolves into a space-time with temporal directionality. The profound implication here is that the universe does not begin in time, but with time. Time is not an eternal backdrop onto which events are painted. It's something that emerges, a direction born out of quantum conditions like warmth rising from coals that were once merely cold matter. This eliminates the need for a singularity. It also eliminates the need to ask, what came before? Because there was no before in the traditional sense. There was no sharp line to step across, only a smoothing, a turning, a kind of quantum rounding. The term no boundary is key. It doesn't mean the universe is infinite in size. It means it has no edge in time. Just as the Earth's surface is finite but has no boundary, you can fall off. The early universe is thought to be finite but without an edge in the past. The cosmos in this model is self-contained. It has a shape, but not a limit. This doesn't mean there aren't mysteries left. The no-boundary proposal is difficult to test directly. It arises within a broader framework of quantum gravity that remains, even now, largely speculative. We don't have a complete theory of how quantum mechanics and gravity play together at the Planck scale, but what the proposal offers is a coherent, consistent way of thinking about the universe that removes the most troubling paradoxes of the Big Bang. It also opens a poetic space, a kind of intellectual sanctuary, where we can stop asking, what lit the fuse, and begin asking, what shape did the quietness take before the first sound? In interviews and lectures, Hawking often spoke of his desire to replace the idea of a creator, not necessarily to deny it, but to remove the necessity for it in physics. The no-boundary proposal was part of that effort. If the universe has no edge in time, then it doesn't need a first cause. It simply exists. It simply becomes. It doesn't explode into being. It unfolds from conditions that were always present, even if they defy our intuition. And yet, despite this radical reframing, the no-boundary model is not cold or mechanical. There is a quiet beauty in it. The idea that the cosmos emerges not with drama, but with a curve, not with a strike of lightning, but with the soft geometry of a closed loop. In a way, it brings physics closer to art, to sculpture. The universe becomes something shaped, not started, something rounded, not ruptured. As we look back through the telescope into light that has travelled for nearly all of time, we may be seeing not the flicker at the end of a long fuse, but the beginning of a smooth hill, curving down into our present. And at the top of that hill, if we could reach it, there would be no cliff. Only the quiet continuation of something that was never meant to be interrupted. The no-boundary proposal doesn't tell us why there is something rather than nothing, but it does suggest that nothing may never have existed in the first place, that the cosmos did not emerge from void, but from shape. That time was not imposed. It was grown like a path unfolding in the forest of existence. And if that's true, then our universe is not a product of abrupt invention, but of gradual becoming. Not the striking of a bell, but the soft ringing that continues long after the hand has left it. We think we know what time is. We feel it, measure it, live by it. It runs through our clocks, our calendars, our memories. We watch it pass in quiet moments, track its urgency and deadlines, feel its weight when we reflect on age. Time, to us, is like water, something that flows past us, steady and irreversible. But what if time isn't flowing at all? What if it's not even real, at least not in the way we imagine it? What if space and time are not the canvas on which reality is painted, but products of the painting itself? This is the radical and increasingly serious idea behind some of the most cutting-edge work in theoretical physics. That space and time may not be fundamental ingredients of the universe, but rather emergent phenomena. Things that arise not at the root level of reality, but as consequences, side effects, of something deeper, more abstract and perhaps more informational. It's a startling shift. And yet, as with many startling ideas in science, it emerges not from speculation, but from trying to solve problems that more conventional approaches couldn't fix. At the heart of this shift is a question physicists have been asking for decades. How do we reconcile quantum mechanics, which governs the very small, with general relativity, which governs the very large? These two pillars of modern physics are deeply successful in their own domains, but fundamentally incompatible when pushed to their extremes. They treat space and time differently. In relativity, space-time is a dynamic stage, a fabric that bends and warps with mass and energy. In quantum theory, time is just a background parameter, fixed and absolute. Something doesn't match. Enter the idea of emergence. In everyday life, we already understand emergent properties. Wetness, for example, is not a property of a single water molecule. A single molecule is neither wet nor dry. Wetness arises only when countless molecules interact in specific ways. Temperature is similar, not something possessed by a particle, but a statistical measure of energy across many particles. These are properties that only appear when you zoom out. Some physicists now believe that space-time itself might be like that. It's not fundamental, but arises when deeper elements, perhaps quantum entanglement, perhaps informational structures, are organised in the right way. Zoom in far enough, and you won't find space. You'll find a network, a web, a lattice of relationships. This line of thought has led to an extraordinary insight. Entanglement builds space. This idea became prominent through the work of theorists like Mark van Ramsdonk, who explored how increasing entanglement between regions of quantum fields could actually cause space to connect. In his now famous 2010 paper, he proposed that space-time geometry is a direct result of entanglement patterns. Remove the entanglement and space itself dissolves. It's as though what we perceive as distance or direction is just a map of which quantum bits are in relationship with which others. Geometry is not carved into the universe like grooves in stone. It's drawn dynamically from the invisible threads of connection. This connects, intriguingly, to ideas like the AD-SCFT correspondence or holographic duality, where a lower dimensional quantum field theory on a boundary surface can fully describe the gravitational physics of a higher dimensional space within. In such models, space-time, and everything within it, is encoded on a kind of informational screen. Our universe may be holographic not in the sci-fi sense, but in a rigorously mathematical one. And if space can emerge from quantum information, then time might as well. Here things get even stranger, because time, more than space, feels absolute to us. It's built into our language, our emotions, our sense of self. But in certain interpretations of quantum mechanics, such as the Page-Wooter's mechanism, time emerges not from an external ticking clock, but from correlation. In a timeless quantum universe, change still happens, but it's measured by how one system shifts in relation to another. You only perceive time because you're part of the system watching another part evolve. Time, in this view, is a story told by correlations. This means that what we experience as temporal flow might be just a narrative, assembled from relationships between quantum states. Events don't happen in time. They are timing itself. In a way, we're not travelling through time. We're constructing it, piece by piece, as we perceive changes in ourselves and the universe around us. Such ideas don't just reshape physics, they reframe what it means to exist. If time and space are not foundational, then reality itself is not a place or a moment, but a network of relations. The world is not made of things in locations, but of interconnections, entangled meanings, and fluctuating patterns of correlation. And our consciousness, the part of us that feels rooted in now, may be a node within that network, tuned to a specific story woven from those correlations. This might also explain why we struggle so deeply with the idea of a universe without a beginning. We're narrative creatures. We live by sequence. We think in arcs. But if time itself is not a fundamental feature of the cosmos, then trying to locate a first moment may be as misguided as trying to find the topmost point on a circle. It's only the shape of the path that matters, not where you started. And in this view, all our questions about the start of the universe become something else entirely. Not when did it begin, but how did the illusion of a beginning emerge? Not what happened first, but what structure of relationships made that question feel meaningful? These aren't just abstractions, they matter. Because when we look at the earliest galaxies and see organisation where there should be chaos, maturity where there should be infancy, we may not be seeing errors. We may be seeing proof that the very fabric we're trying to measure is woven from something else, and that the loom doesn't use time as its thread. In such a universe, maybe we don't need a beginning. Maybe we need only a pattern, one rich enough to contain meaning, varied enough to contain wonder, and gentle enough to allow rest. Science is not a straight road. It twists, pauses, meanders. For every theory that leads us forward, there are many that branch off, some discarded, some ignored, some quietly forgotten in the pages of old journals and the corners of abandoned lecture halls. But sometimes, in the light of new mysteries, it's worth returning to those neglected trails. Not because they were right, but because they remind us of something important. The universe has always been stranger than we expected, and humility is a better guide than certainty. In the early 20th century, long before the cosmic microwave background had been discovered, and decades before the phrase Big Bang became mainstream, there were competing ideas about the nature and origin of the universe. One of the most famous was the steady-state theory, proposed by Fred Hoyle, Thomas Gold and Hermann Bondi in 1948. Their model held that the universe had no beginning and no end, that it looked the same in all directions, not only in space, but in time. As the universe expanded, new matter was continuously created to maintain a constant density. Galaxies aged and drifted away, but new ones formed in their place. It was a cosmos without birth or death, eternal, unchanging in its overall structure. The appeal of the steady-state model was philosophical as much as scientific. It offered a kind of timeless elegance, avoiding the thorny question of creation altogether. There was no singularity, no before, no first moment, just a universe that had always been, and would always be. But when the cosmic microwave background, CMB, was discovered in 1965, a faint afterglow from a hot, dense early phase, the model lost credibility. The CMB was a fingerprint the steady-state theory could not account for. Observations of evolving galaxy populations also contradicted the idea of temporal uniformity. Gradually, cosmology turned away, and the theory was shelved. Yet, for all its shortcomings, the steady-state theory left an imprint, a reminder that we once dared to imagine a cosmos without beginning. Another forgotten avenue was plasma cosmology, a bold alternative championed most notably by Nobel laureate Hannes Alf Venn. This model proposed that the large-scale structure of the universe is not shaped primarily by gravity, but by plasma, the electrically conductive state of matter that makes up 99% of the visible universe. In this view, electromagnetic forces, especially those described by magnetohydrodynamics, play a central role in cosmic evolution. Galaxies, filaments, and voids are not merely pulled together by gravity, but sculpted by electric currents and magnetic fields interacting across vast distances. Plasma cosmology was compelling for several reasons. It relied on laboratory-tested physics. It explained the filamentary structure of the universe in terms of plasma dynamics, something we still observe in interstellar and intergalactic media. Yet, despite its strengths, the theory fell out of favour. It struggled to explain the observed uniformity of the CMB and the abundance of light elements. And while magnetic fields are undoubtedly important in the universe, the theory couldn't match the predictive power or observational success of the Big Bang framework. Still, many of its insights survive in modern astrophysics, particularly in how we understand galactic jets, solar flares, and cosmic plasma behaviour. Alf then may have been wrong about the big picture, but right about many details. Then there is tired light, a simple, elegant idea proposed by Fritz Zwicky in the 1920s, in response to Edwin Hubble's observation that distant galaxies appeared redshifted. In the Big Bang interpretation, redshift results from the expansion of space itself. Galaxies are receding, and their light is stretched as the cosmos grows. But Zwicky suggested a different explanation. Perhaps photons lose energy as they travel vast cosmic distances, not because space is expanding, but because the photons themselves are tired, interacting with matter or fields in subtle ways that cause them to shift toward the red end of the spectrum. Tired light offered a universe that was static, eternal, and non-expanding. The redshift in this view was not a velocity, it was a fading. But as appealing as the idea was, it soon ran into trouble. Tired light predicted certain distortions and blurring of distant objects that were not observed. It couldn't account for the time dilation seen in supernova light curves, and it failed to predict the detailed structure of the CMB. Like the others, it was largely abandoned, and yet these discarded ideas have not vanished entirely. In recent years, especially in light of the surprising results from the James Webb Space Telescope, galaxies appearing too developed too early, some scientists and thinkers have revisited these alternatives, not to reinstate them wholesale, but to ask, were there insights in these models that we too quickly ignored? For example, could some form of photon interaction be influencing redshift in a way we don't yet understand? Could electromagnetic forces play a larger role in cosmic structure than we have modelled? Might the steady state's rejection of a singular beginning find renewed relevance in cyclic or emergent cosmologies? Of course, these aren't mainstream views, but the beauty of science is that it is not, at its best, a consensus. It is a conversation. A model is not a truth, it's a lens. And when that lens begins to distort, when it no longer fits the observations it was built to explain, it is time not always to abandon it, but to revisit the alternatives, to ask again what we thought we knew, and to listen patiently to voices we once thought were silenced. In these forgotten theories we may not find the answers, but we may find the courage to ask better questions, the humility to remember that even wrong ideas can carry seeds of truth, and that the universe, in its vastness, has always defied easy conclusions. It is not always in the cutting edge where revelations lie. Sometimes it's in the pages we didn't finish reading. For nearly a century, we've lived in a universe that's growing, not in mass or complexity, but in space itself. An expansion not like a balloon filling with air, but more like the balloon's rubber stretching outward, carrying galaxies with it. This idea that space itself is expanding underlies modern cosmology. It explains the redshift of galaxies, the cooling of the cosmic microwave background, the apparent age and size of the cosmos. It is the backbone of the standard model, and yet, like any good structure, it relies on assumptions. And now, with new eyes, golden and floating in space, we're beginning to ask, are those assumptions still holding? The James Webb Space Telescope was expected to reveal small, clumpy early galaxies, fragments of cosmic structure still in their formative years. Instead, it showed something almost unsettling. Galaxies that were massive, organised, and rich in heavy elements, far earlier than expected. It wasn't just that they appeared quickly, but that they appeared already aged, mature, built, and that throws a quiet wrench into the expanding universe timeline. To understand why, we need to revisit what redshift actually means. Redshift, as observed in astronomy, is a shift of light toward longer wavelengths, toward the red end of the spectrum. When we look at distant galaxies, their light appears redder than it would if they were nearby. In the standard interpretation, this redshift is caused by the expansion of space itself. As photons travel across the cosmos, the space they move through stretches, and so does their wavelength. It's not that the galaxies are moving through space, it's that space is growing between us. This idea, called cosmological redshift, is not merely Doppler shift. It's a feature of the metric expansion of the universe, and yet it depends on a key assumption, that the geometry of the universe and its expansion history are well understood. But if the galaxies we're now seeing formed earlier and faster than this model allows, then perhaps redshift doesn't tell us quite what we thought it did. Some researchers have gently suggested that we revisit this foundational assumption. Could it be that redshift, at least in some part, reflects not distance or velocity, but something else? Perhaps interactions we don't yet fully understand, perhaps a more complex geometry, or even, as some fringe theories propose, that photons lose energy through as yet unexplained processes as they travel, subtly mimicking the effect of expansion. Such ideas are not mainstream, but neither are they absurd. They echo the old tired light hypothesis, yes, but they also intersect with new theoretical frameworks in quantum gravity and information theory. In some models, redshift could contain contributions from the underlying structure of space-time, perhaps something fractal or foamy, or influenced by quantum fields on vast scales. In others, the universe may not be uniformly expanding, but doing so unevenly, more like a crumpled sheet than a smooth balloon. Or perhaps the issue lies not in the nature of redshift, but in our interpretation of time. If the early universe behaved differently, if time itself flowed at different rates under different conditions, then galaxies might appear older than they should be, not because they truly formed earlier, but because our cosmic clock is miscalibrated. What if cosmic time isn't a single, universal beat, but a symphony of local rhythms? Another possibility, the universe may be larger or older than we think. The 13.8 billion year estimate is based on models that fit observed data within certain assumptions. But if those assumptions shift, if the expansion rate has changed more than expected, or if early acceleration wasn't accounted for, the true age and scale of the cosmos might extend far beyond current estimates. In such a universe, early galaxies might not be early at all, just distant and complex within a much broader, older cosmos. There's also the quiet question of curvature. The universe, in standard models, is treated as spatially flat, based on measurements of the CMB and large-scale structure. But what if this flatness is only approximate? A universe with even slight positive curvature would eventually loop back on itself. Light could take multiple paths, distances could be deceptive, and what appears to be ancient might be close, bent by the geometry of a closed cosmos. And then there's a more radical idea, that the universe is not expanding at all, or not in the way we think. In some fringe yet carefully constructed models, the cosmos is static or cyclic, and redshift is an emergent effect, a symptom of underlying relational changes between quantum fields or particles rather than expansion. These models remain highly speculative, but they underscore the point. What we take as foundational might, under certain conditions, be merely apparent. So, is the universe really expanding? The best answer, the most honest one, is still yes, according to the data we have and the models that fit it. But the word really carries weight. It suggests an absolute reality, independent of models, measurements, or metaphors. And in cosmology, that's a dangerous illusion, because every observation is filtered through our instruments, our interpretations, our assumptions. Perhaps the expansion of the universe is real, but not complete. Perhaps it's real, but only within certain scales or epochs. Or perhaps, like so many things in science, it's a stepping stone, useful, powerful, predictive, but not the final shape of truth. What James Webb has given us is not a contradiction. It's a pause, a quiet, shimmering hesitation in the story we thought we were telling. And in that pause, we're reminded that the universe doesn't owe us clarity. It only offers us wonder. And sometimes, wonder means being willing to ask again what we thought we had already answered. Not to undo, but to unfold. Not to reject, but to reimagine. And not to prove, always, but simply to observe, carefully, curiously, patiently. Because even in a universe that stretches, bends, or loops, curiosity expands faster than anything else. There are moments in science when certainty begins to crumble, not in a dramatic collapse, but in a quiet erosion. A familiar model starts to feel stiff. The answers that once clicked neatly into place now wobble under new light. And while this can be unsettling, it can also be the beginning of something beautiful. Because when answers weaken, questions strengthen. And from that soft undoing, curiosity is reborn. For decades, cosmology has moved forward with a kind of determined confidence. The Lambda cold dark matter model, Lambda cold dark matter, has served as a trusted map. It describes a universe born in a singular hot origin, one that expanded, cooled, formed stars and galaxies, and now accelerates outward under the mysterious push of dark energy. It is a model built on equations, data, and an elegant logic, and it has succeeded. It predicted the cosmic microwave background, the abundance of light elements, the large-scale structure of galaxies. But now, like all models that live long enough, it faces questions it cannot easily answer. James Webb did not break the model. It simply reminded us that no model is permanent. And in that reminder, a space has opened, not just for alternative theories, but for deeper inquiry. The kind of inquiry that is less about getting the right answer, and more about learning how to ask better questions. What's unfolding now is not a crisis in cosmology, it's a renaissance. We're seeing a renewed interest in foundational thinking, not just tweaking parameters, but revisiting assumptions. Scientists are dusting off old notebooks, rereading papers they once set aside, and asking if there might be something left inside them. Not a solution, but a seed. Younger researchers are less bound to tradition, more willing to blend physics with philosophy, observation with imagination. There's a new generation that isn't afraid to ask, what if? Not as a challenge, but as a form of wonder. The scientific method, after all, is not a checklist. It's a stance, a posture of openness, a willingness to let nature surprise us. It's easy to forget that the models we rely on, elegant, precise, and deeply explanatory, are still just scaffolding. They help us reach higher, see further, hold up our understanding, but they are not the building itself, and every so often we need to pull them down or climb off of them to see what lies beneath. There's a kind of vulnerability in this stage of science, to stand in front of data that doesn't fit, to admit that we don't know, that we've assumed, that we may have to let go. But there's also immense strength in that, because the willingness to be wrong is the beginning of real discovery. Cosmology is not just physics, it's also storytelling. And now we're realizing we may have been using the wrong structure. Maybe the universe isn't a novel with a beginning, middle, and end. Maybe it's a poem, cyclical, layered, suggestive, or a painting, abstract, not meant to be solved, but felt and interpreted again and again. Maybe it's more like music, with rhythms and harmonies and notes that repeat, but never in the same way. When we ask if the universe had a beginning, or if it's expanding, or if time itself is real, we're not just probing the cosmos, we're probing the way we think. We're asking what it means to observe, to explain, to understand. And those are not questions that end in answers, they end in better questions. In this spirit, the theories on the edge, tired light, steady state, bouncing cosmologies, emergent time, are not heresies. They are reminders. They show us the outer edges of imagination. They mark the boundary where ideas begin to shimmer, not because they're wrong, but because they haven't been fully seen yet. Even if these ideas never become dominant, they serve an essential role. They shake the ground just enough to make us test our footing, and they whisper, gently, insistently, that the universe is still vast enough to surprise us. Already, new telescopes are on their way. The Nancy Grace Roman Space Telescope, the Vera Rubin Observatory, the extremely large telescope, the Laser Interferometer Space Antenna, each one promising to stretch our senses even further. Each one a new set of eyes, listening for something we didn't know how to hear. Together they form the next movement in this quiet symphony of seeking. What we're entering may be a new golden age of cosmology, not because we have answers, but because we've remembered how to wonder. The frontier is no longer just at the edge of the observable universe. It's here, in the questions themselves, in the act of asking. So if you're watching this now, quietly, perhaps just before sleep, know that you are part of this renaissance. Not a passenger, but a participant. Because curiosity is not the property of scientists alone. It belongs to anyone who looks up and asks softly, "What if?" And perhaps that's the most beautiful thing of all, that in the universe where time may not be real, where beginnings may never have existed, and where even space could be an illusion, the question remains. And as long as we have the courage to ask it, the cosmos will answer, not with certainty, but with depth, not with maps, but with stars. You always wake up facing forward. Even before your eyes open, your thoughts reach into the day ahead, never back into the night behind. We remember the past, but never the future. We age. We gather stories in one direction only. This, to us, is time. A river, always flowing, never reversing. But physics, quietly and insistently, suggests something different, something stranger. The arrow of time, it turns out, may not be part of the laws of nature. It may be something we stitch into the fabric after the fact, a story we tell ourselves, not a feature of reality itself. At the heart of this question is entropy, the measure of disorder in a system. When we say time moves forward, what we often mean is that entropy increases. A teacup shatters. A cold spoon warms in hot tea. Memories are made, not unmade. These are all examples of systems moving from order to disorder, from low entropy to high, and this increase is what gives time its direction, at least in the way we experience it. But this arrow, from past to future, is not written into the fundamental equations of physics. Newton's laws, Maxwell's equations, even the Schrödinger equation of quantum mechanics, they are time symmetric. You can run them forward or backward, and the math still works. There's nothing in the core mechanics that insists time must move in one direction. So why then do we feel it so strongly? It might be that the arrow of time is statistical, not absolute. Imagine a freshly shuffled deck of cards. There are more ways for the cards to be disordered than ordered, vastly more. So any small random shuffle tends to lead away from order, not because it's forbidden to go back to order, but because it's so unlikely. The same is true in thermodynamics. The past had low entropy. The future, probabilistically, will have higher entropy. And so, forward we go. This means our sense of before and after is not a universal truth. It's a consequence of living in a corner of the universe where entropy started low and has been rising ever since. Had we evolved in a high-entropy universe, where there was no clear difference between then and now, perhaps we wouldn't perceive time at all, or we'd experience it as fog, not arrow. But there's more. If entropy defines the direction of time, and if entropy is about information, then time might be a story about information loss, or perhaps information change. And this suggests that time may not exist outside of systems with memory. Time becomes something that emerges only when bits can shift, when states can change, when history becomes relevant. This leads to a quiet but radical idea. The universe as a whole might not have time, not in the way we do, on the larger scale, taken as a complete quantum system. There may be no now or then, there may be no passage, no flow. The universe might simply be timeless, static, not frozen in the sense of stillness, but complete, like a landscape seen all at once. In this view, what we experience as the passage of time could be the way a local observer, like you, perceives unfolding correlations. You're not moving through time. You're watching different slices of the universe light up in a particular sequence, one that feels linear, but might not be universal. It's like flipping through a photo album. The pictures are all there, but your awareness moves from one to the next, building the illusion of a journey. If this sounds abstract, that's okay. It is, but it's also deeply connected to daily life. Every moment of remembering, every glance backward, carries this arrow. You cannot remember something that hasn't happened yet. Your body ages in one direction, and every time you stir a cup of tea, the swirl moves not just in space, but in entropy, toward a state of rest, of disorder, of equilibrium. And yet, something in us resists equilibrium. We strive, we build, we try to create meaning out of temporary arrangements. This might be why time feels so powerful, not because it flows, but because we are aware of what it takes from us. Every moment we live, something ends, something slips, something vanishes into the category of was. That ache, that subtle pressure, may be what we call the future. There's a philosophical comfort, though, in the idea that the arrow of time is not cosmic law, but local condition. It means that what we feel as inevitable might not be universal. It might be the side effect of a statistical hiccup, a particular arrangement of the early universe, an entropy curve we happen to be sliding down. It suggests that what we call time might be just one way of reading the universe, and not the only one. Some physicists, and philosophers, have even speculated that if we were able to view the universe from a different angle, perhaps from outside of time, we might see all events as coexisting, not sequenced but scattered, not a film but a painting, and in that painting nothing is lost. Every moment still exists, even the ones we can no longer touch. The first breath you took, the smile of someone long gone, the quiet hours before something changed. They may not be reachable, but perhaps, in a deeper structure of reality, they are still there. Time, then, is not an enemy, or a river, or a god. It is lens, and lenses can distort, magnify, or fade. But they can also focus, and in this focused attention, in this moment where you sit and listen and feel the pull of past and future, you are doing something extraordinary. You're experiencing the illusion of time, knowing it is an illusion, and yet still loving it, still walking through it, still calling it home. And maybe that's enough. When you wake up in the morning, you might think of yourself as a body in a room, on a planet, beneath a sky, a small point in a vast space. But there is another way to understand what and where you are. One that doesn't start with physical location, but with connection. A theory where reality isn't built from particles or waves, but from relationships. Where what truly exists isn't things, but the information that binds them together. It's an idea that has quietly grown through the foundations of physics for decades, And now, more than ever, it's beginning to change everything we thought we knew about space, time, and being. This is the world of quantum information theory, and at its heart is a quiet revolution. The idea that the most basic element of the universe is not matter or energy or even space, but bit. The binary yes, no, the fundamental unit of information. It's a shift from substance to structure, from presence to pattern. Physicist John Archibald Wheeler, a pioneer of relativity and quantum gravity, famously summed this up in a phrase that feels more like poetry than physics: it from bit. In other words, every it, every particle, field, event, or object arises from underlying binary choices. A deep web of yes or no questions, forming the scaffolding on which everything else is built. You are not merely atoms and molecules. You are the product of information organised in a particular way, a living pattern in a sea of probabilities. In this view, space and time are not fundamental containers, but emergent properties of these relationships, like how the image of a face emerges from pixels on a screen, or how temperature emerges from the average motion of molecules. They are not objects themselves, they're ways of organising perception. One of the most compelling pieces of evidence for this comes from quantum entanglement, a mysterious phenomenon where two particles, once linked, remain connected across vast distances. Measuring one instantly affects the state of the other, no matter how far apart they are. It's not that information travels between them, it's that they were never truly separate. Their correlation existed before space was assigned to them. This has led some physicists to propose that entanglement is the fabric of space, that what we call distance is just a way of describing how much, or how little, two systems are entangled. The more entangled they are, the closer they feel. The less they share, the further apart they seem. Space then becomes a map of entanglement patterns, not a fixed arena. Mark van Ramsdonk, a theoretical physicist, suggested that if you start with a universe where nothing is entangled, you don't get empty space. You get nothing at all. But as you increase the entanglement between regions, space begins to emerge. It's as if the universe is woven from invisible threads made not of string or particle, but of mutual knowledge, shared uncertainty. And if space is entanglement, what about time? Here, the picture becomes even more subtle. In certain interpretations of quantum theory, time doesn't exist as a flowing river. Instead, it arises from correlations between events, the comparison of one quantum system to another. The page-router's mechanism, for instance, imagines a universe where the total system is static, timeless. But if you split it into subsystems, an observer, and a clock, then time appears. Not because it was already there, but because of how the parts relate to one another. In this sense, you are not in time. You are a node in a structure where time emerges from the act of observing. Time is what you feel when you're entangled with the world, when you register change, memory, difference. It is not a thing you move through. It's a pattern you participate in. What does this mean for you, sitting here listening quietly to these words? It means you're not just a being in a universe. You're of the universe, a specific pattern of correlations flickering gently in the quantum web. Your thoughts, your body, your memories. They are arrangements of information not separate from space and time, but co-creators of it. You're not a separate dot on a cosmic map. You are the map, reshaping itself in real time, interpreting and being interpreted. It also means that the boundaries we take for granted, between self and other, near and far now and then, may be illusions born of limited perspective. When you remember something, you reach back through patterns of stored information. When you anticipate, you forecast how systems will evolve. All of this is relational. Nothing happens in isolation. Even identity, the sense that you are a single, continuous self, may be more about informational consistency than physical continuity. A braid of memories, sensations, stories, all held together not by a string, but by coherence. If something remembers being you and behaves in ways you would expect, we call that you. But in a universe made of information, that definition becomes fluid. You're not just located in one place or one moment. You're a shape in the flow, a ripple in the fabric. And what does this mean for the universe itself? It might mean that nothing truly begins or ends. Only patterns shift. Some fade, some stabilize. Some, like galaxies or people, flicker briefly before dispersing. But the underlying information may remain, reshaped, redistributed. Perhaps there is no creation ex nihilo, no making from nothing, only the endless reconfiguration of structure over and over again. It's a quiet view, less dramatic than fireballs and beginnings, but in some ways more intimate. It suggests that to understand the universe, you don't need to look outward forever. You can look at the way things relate, the way a sentence leans into memory, the way a hand brushes against a mug, the way two minds entangle through a shared question. All of that is reality, and it may be all there ever was. If the universe never had a beginning, then perhaps we're not on a path that started somewhere. Perhaps there is no origin to walk back toward, no line to trace to its point of first spark. Instead, we might be standing inside something that simply is, not in the sense of simplicity, but in the older, deeper sense. Existence without edge, time without birth, a cosmos not moving from nothing to something, but simply unfolding within itself, endlessly, like a thought that doesn't begin and doesn't end, but just continues. To sit with this idea is not easy. It unravels the narratives we've built into every corner of human life. We are beings of stories. We define meaning through arcs, beginnings, middles, endings. We mark time with milestones, memories, transitions. We learn through cause and effect, and we make sense of ourselves through the idea of change. If we take away the beginning, if we peel back that first page and find no blankness, only more story, then what happens to our sense of direction, to our sense of self? Some philosophers and scientists suggest that this discomfort isn't a flaw in the theory, it's a reflection of us. That perhaps the reason we seek beginnings is because of how our biology is wired. Our brains evolved to find patterns, to anticipate threats, to make predictions. We track sequences. We remember pain so we can avoid it. We understand a moment not in isolation, but in relation to what came before and what might come next. Time, in that sense, is not just a feature of the cosmos, it is a feature of consciousness. And that brings us to a soft but powerful realization. Maybe some of our biggest questions are shaped more by how we think than by what the universe is. What was the beginning? Where did we come from? Why are we here? These are not just scientific inquiries, they are cognitive structures, questions formed by the way our minds process change, memory, and awareness. When we ask them, we're not just exploring the universe, we're also exposing the architecture of our own perception. A being without memory might never ask where it came from. A being without projection might not wonder what comes next. Even in physics, the questions we ask are shaped by the tools we have. Not just telescopes and equations, but also the assumptions we carry. The Big Bang, for all its elegance, was always a model. A story that fits the evidence. But so were the models before it, and perhaps so will be the ones that come after. Every era has its cosmology, and each one says more about its creators than we care to admit. This isn't to say the questions are wrong, they are sacred in a way. They bind us together across centuries and civilizations. But perhaps they are not meant to be answered, only lived with, held gently, like a candle in a quiet room, not because we expect it to light the entire sky, but because it reminds us that we are astonishingly here. Science, at its best, walks this delicate line. It asks boldly, but it also listens. It tests, but it also marvels. And when it finds that the answers have grown slippery, it does not panic. It pauses, and it wonders. In the case of cosmology, we are now standing at the edge of what might be a new kind of question. Not one that seeks a first cause, but one that seeks to understand why we ask about first causes at all. Not what came before the universe, but what does it mean to speak of before? Because in a universe where time may not be fundamental, where space may be woven from information, where beginnings may be illusions formed from entropy and memory, perhaps the real mystery is not out there, but in the asking itself. And maybe that's where science and philosophy meet, not in their methods, but in their willingness to sit at the edge of unknowing, to say, here is a question so large, so strange, that even our words begin to dissolve when we approach it. And yet, we approach anyway. Because even without answers, there is something in us that wants to lean into the unknown, to gaze into the sky not for what it gives us, but for what it draws out of us. A feeling, a whisper, a recognition that we are small, yes, but not meaningless. We are not accidents of matter. We are participants in wonder. And perhaps if the universe truly has no beginning, then neither does our curiosity. It too might be eternal. Not because it reaches an end, but because it doesn't need one. It is not a path, it is a presence. So let us stand for a moment on the edge of that presence, not rushing to leap forward, not demanding closure, just breathing quietly in the soft space between knowing and imagining, letting the question echo, not for an answer, but for the beauty of its sound. When the James Webb Space Telescope opened its golden eyes to the sky, it changed the rhythm of cosmic inquiry. Its first images were not just beautiful, they were unsettling. Galaxies too mature, too soon. Stars with heavy metals before heavy metals should have had time to form, and a quiet message woven into every photon. The universe may not be as young or as simple as we once thought, but James Webb is not the final word. It is the prelude to a chorus, the start of a symphony still being tuned. The sky is full of secrets, and the instruments we need to hear them are already being built. One of the most anticipated players in this next movement is the Nancy Grace Roman Space Telescope, often called Webb's wide-eyed cousin. Where Webb peers deeply into small patches of sky, Roman will scan vast swathes, watching not just what is, but how things change. Roman will study the mysterious dark energy that seems to stretch the universe apart. It will map the cosmos in infrared light, hunting for faint galaxies and the ripples of gravitational lensing, distortions in space-time itself. And perhaps, in those distortions, we will see not just galaxies bent by gravity, but models bent by data. Perhaps Roman will find evidence that expansion is not as smooth as we think, or that structure formed earlier than models allow, gently nudging us towards something new. Closer to Earth, but just as ambitious, the Vera C. Rubin Observatory in Chile is preparing to capture the changing sky. Its legacy survey of space and time, LSST, will photograph the entire visible night sky every few nights, over and over again, for a decade. It's a telescope built not for stillness, but for motion, for catching supernovae, asteroid paths, flares, and flickers, for seeing the tempo of the cosmos, not just its shape. Rubin's data will be vast, petabytes of it, and in those patterns we may find new anomalies, subtle drifts in brightness, or position that hint at deeper truths. A gravitational wave here, a transient there, each an echo of something we don't yet understand. Then there's the extremely large telescope, and yes, that is its actual name. Set to be the most powerful ground-based telescope ever constructed, with a mirror over 39 meters wide, it will bring an unprecedented sharpness to our view of distant galaxies. Where Webb reveals that early galaxies exist, ELT will dissect them, mapping their stars, their metals, their rotation, their mass. If those galaxies are truly too complex for their supposed age, ELT may offer the fine detail needed to force cosmology's hand, to refine or even redefine our timelines. It's one thing to see something strange, it's another to measure it so clearly that the model has no choice but to yield. And then, further out, both literally and conceptually, is LISA, the Laser Interferometer Space Antenna. A gravitational wave detector in space, LISA won't see light at all. It will listen to the vibrations of space-time itself. While ground-based detectors like LIGO have already caught the trembling of merging black holes, LISA will catch longer, slower waves, signals from sources billions of years old. It may detect the gravitational murmurs of primordial black holes, or even echoes from events before the Big Bang, if such things left any imprint. It might help us understand how structure arose from what seemed like formlessness, or whether the early universe had a different rhythm entirely, perhaps cyclical, bouncing, or braided. Each of these instruments carries its own song. Roman listens in broad infrared harmonies. Rubin plays a steady percussive rhythm of repeating images. ELT offers the fine strings of sharp optical analysis. And Lisa hums a deep bass, almost too low to hear, but capable of shaking the frame. Together they compose something more than observation. They compose anticipation. Because the questions that James Webb reawakened about time, formation, causality, emergence are not going away. They are becoming more refined, more precise, and more courageous. What these upcoming missions share is not just new data, but a willingness to unsettle, a design that embraces the unknown rather than fearing it, a scientific humility that doesn't treat surprise as a flaw, but as a signal. This is what a new golden age of cosmology might look like. Not a rush toward a final theory, but a return to foundational curiosity. A time when questions are not stepping stones to answers, but destinations in themselves. What if redshift is more complex than we assumed? What if structure forms faster, or under different rules? What if the universe never really began? It just crossed a threshold of visibility. And what if we're only now developing the ears to hear that first whisper? In the decades to come, as Roman sweeps the sky, Rubin captures the flickers, ELT sharpens the ancient light, and Lisa listens in silence. We may not find confirmation of our current models. We may find something more precious. Tension. The place where data and theory don't quite align. The small, persistent mismatches that say gently but firmly, look again. Because looking again is the heart of science. It is the decision to not be satisfied with the story we know, and it is the faith, quiet, steady, sometimes trembling, that the universe still has more to say. The future of cosmology is not just bright, it is wide. It stretches not only forward in time, but inward toward meaning. These instruments will scan the sky, but in their reflections we may also see ourselves, still wondering, still listening, still beautifully unsure. When you look up at the night sky, maybe from a balcony, a forest trail, or just a quiet corner of your thoughts, the stars do not give answers. They do not whisper truths or recite equations. They simply shine, softly, indifferently, beautifully. And yet in that silence something inside you leans forward. A kind of reaching begins. A question, not always fully formed, starts to glow alongside the stars. It doesn't ask to be answered, it only asks to be held. That, perhaps, is the deeper purpose of cosmology. Not to solve the universe like a puzzle, but to encounter it as a kind of mirror. One where every discovery is also a rediscovery of how we wonder, of what we fear, of the places inside us that feel stretched between mystery and meaning. We have talked about redshifts and timelines, about entropy and emergence, about photons stretched thin across time and gravitational murmurs too deep for ears. We've journeyed into theories where time has no edge, and others where space is made not of distance, but of relationship. But maybe now is the time to pause and to ask something softer. Why do we ask at all? Because in truth, these cosmic questions often fold back into human ones. When we wonder whether the universe had a beginning, we're also asking what it means to begin, to be born, to emerge from nothingness. When we ask how long the universe has existed, we're also asking how long we will exist, what it means to end, and whether anything of us remains in the vastness. These are not just scientific questions, they are deeply personal ones, and science, for all its methods and models, is not separate from the human experience. It grows out of it. The telescope was not born from neutral curiosity. It was born from longing, the same longing that paints galaxies in nursery ceilings and etches constellations into cave walls. To observe is to love, in a way. To look carefully at something that cannot look back and still feel, somehow, that connection has occurred. So perhaps it's no surprise that the more deeply we observe the universe, the more deeply we come to observe ourselves. The better our telescopes become, the more we see, not just ancient light, but ancient emotion. A kind of quiet courage wrapped around every question we dare to ask. Because these questions, where did it begin? What is it made of? How does it end? They all carry within them another more hidden question. What am I in all of this? And maybe that question has no final answer. Maybe it isn't supposed to. Maybe that's what makes it powerful. Not its resolution, but its repetition. The fact that we can ask it again and again, in new lights, in different times, and still find it filled with wonder. Maybe that's what makes a question whole. Not its clarity, but its capacity to grow alongside us. There is an idea in philosophy and in physics that we don't just discover the world, we also create the lens through which we view it. The questions we ask shape the answers we're able to hear, and so the act of asking becomes participatory. Not passive, but generative. In this view, the universe is not just a stage, it is a conversation. One where silence has weight and presence is a kind of reply. You may not remember all the models, the big bounce, emergent time, ghosts of universes past. You may not remember how the galaxies cluster, or how LISA will float through the cold stillness of space. But what stays, long after the specifics fade, is the feeling of having reached, the sense of having stretched yourself into a space you didn't need to understand in order to feel at home within. And perhaps that's what cosmology gives us. Not certainty, but belonging. A way to locate ourselves, not by position, but by perspective. We are not at the centre of the universe, we never were, but we are at the centre of our own noticing. And that is no small thing. To notice the stars, and to feel their ancient light on your face. To learn that time may not flow, but still to feel it in your chest. To realise that questions do not weaken us, they make us whole. Because in the end, what we seek is not to conquer mystery, but to dwell beside it. Not to hold the universe still in our hands, but to let it pass through us like a song we don't need to understand to love. So let the questions stay open, let them breathe, let them echo, not because they're unfinished, but because they are alive, and let us carry them into sleep, into silence, into the next sunrise, not like burdens, but like small, glowing reminders that we are here, and curious, and not alone. So now, here we are, at the edge of the question, and perhaps at the edge of waking. You've followed a quiet thread through space and time, across deep sky surveys and ancient equations, through stars that lived before they were expected to, and models beginning to feel the gentle pressure of mystery once more. And perhaps your mind is full, not with answers, but with soft echoes. That's all right. That's exactly where we're meant to be. Because this was never a journey towards certainty. It was a way of walking through unknowing, slowly, gently, like passing through a vast field of wildflowers at dusk, where you don't need to name every bloom to feel the peace of their presence. We began with a rupture, James Webb's startling vision of galaxies too grown, too early, too ordered. Not chaotic, not scattered, but luminous and whole, as if the universe had always known what it was doing. They were not supposed to be there, and yet they are. And from that quiet contradiction bloomed a question. What if the universe never had a beginning? What if time did not explode into being, but instead emerged like a reflection, subtle, cumulative, the way light seeps into a sleeping room? What if we've been looking at the story all wrong? Not from the inside of a line, but from the edge of a spiral. We spoke of redshift, of timelines compressed beyond physics, of galaxies too structured for the ages they supposedly inhabited. We wandered through the Lambda CDM model, its triumphs, its tensions, and considered that the models we use are only temporary scaffolding. Helpful, illuminating, but never final. They are like the paths through a meadow, clear for a time then overtaken by new growth. And from there, we stepped beyond consensus, into the terrain of forgotten ideas and radical reimaginings, the big bounce where universes breathe in and out, plasma cosmology where electricity might stitch the cosmos, tired light where photons wear down across the void, models not discarded perhaps but sleeping, waiting for the right kind of question to wake them again. But the deeper steps came after, when we allowed science to look back at us, not just as observers, but as participants, when we considered time not as a ticking arrow, but as a habit of memory, entropy as a storyteller, entanglement as the architecture of space, the possibility that the universe is not made of things but of relationships, not of moments, but of meaning. And then the quiet thought, almost too soft to say aloud, that the universe taken as a whole might be timeless, that its song does not begin or end but is always playing, that what we feel as flow may be pattern, that what we name as change may be our own reflection. Now, as you lie there, maybe eyes closed, maybe still gently open, the sky above is still stretching, Roman is waiting, Rubin is calibrating, the ELT's great mirrors are being polished, Lisa is dreaming of waves it will one day hear, and through them a new age of questions is quietly approaching. But not tonight. Tonight, there are no instruments humming, no timelines to fix, no models to correct. There is only this moment, this stillness, this soft breath of wonder. Let yourself drift, not into forgetting, but into belonging. You don't have to solve the universe. You don't have to pin it down. All you need is to know that you are part of it, not outside, not above, not separate, but woven in, just like light in a web, just like a note in a song that has no beginning and no final chord. If the universe never began, then neither did you, not in the way we think. You were always on your way here, through stars, through atoms, through stories, through sleep. And even now, as the edge of waking begins to blur, you're still arriving. The galaxies still shine. The questions still echo. And somewhere, in you, the cosmos is still unfolding. Sleep well, little echo from the eternal. You belong to the story even if there was never a first page.